let's go through an example using these 4 big steps that we need to go through running a hypothesis test. So just kind of start fresh with this scenario of we have an antacid that provides relief for 70% of people who use it, and then a pharmaceutical company has a new drug that they want to test, and it's in this wording where they want to test whether it is more effective. There's where we're getting an idea of what's happening in the alternative hypothesis. They run a study with 100 randomly selected patients, 75 people experience relief. So the pieces that we're getting here, this is giving us an idea of what's happened in the past, which links to our null hypothesis. Here they're telling us what we want to test, and that links to our alternative hypothesis. And then what we have here is some sample data. And the sample data never goes into the writing of the hypotheses. This is just telling us what we'll test later on. So what we have here is our null hypothesis that the proportion is 70% is a 0.7. And what we want to prove, we want to test that it is more effective, so we want to see this proportion should be larger than 0.7. So that sets up our hypotheses. We need to go through step 2, which is where we're going to check our conditions and just kind of set up what we're going to be testing. So for independence, we want to make sure that the results are independent. So in this case, it would be that like if one person gets relief from the antacid, is that affecting others? Not really. These results should be independent of each other. And again, you can always use that 10% condition. Let's see, they sampled 100 people. That's less than 10% of all people. So we would have independence there. Randomization, we should be taking a random sample, which they say those 100 people, they're randomly selected. So we're good there. And then we have our sample size condition, which we take our sample size of 100 and we multiply that with our proportion from the hypothesis. So we go to our hypothesis and we apply that 100 to the 0.7 and then 1 minus 0.7, which is a 0.3. So we're getting 70 in this group, 30 in this group, and as long as both of those are more than or equal to 10, we're all good. So we meet our conditions, which means we can use that bell-shaped curve. From there, just a quick little setup. We're using the more than symbol here, which means it's going to be a right-tailed test. If we're trying to prove that things are large, it's going to throw us into the right tail. So what I want to write down here is that we're going to build this curve, and it's going to be our standard normal curve. And when we get our test statistic, if we're running this right-tailed test, our test statistic should be landing to the right. Our sample data should already support what we're trying to find, so our z-score should be landing somewhere over here. And what we're going to want to do is take the area or the probability of that value or even larger. So we want to find this area right here, and that'll tell us our p-value. And something I like to write down here is our rejection rule. What we're going to do is we reject that null hypothesis if our p-value is less than or equal to alpha, which they don't state a significance level here, so that just means we assume it's 0.05. So for this p-value to be small enough, it has to be smaller than or equal to 0.05. That'll mean we have a small p-value, which means we reject that null hypothesis. So this just kind of gives us a setup for when we go through all the steps of finding that p-value. So, first step of finding our p-value is to get our test statistic. So taking p hat minus p from the hypothesis over and our standard deviation using the proportions from the hypothesis. So we have this, but we need our sample statistic. There's which our sample statistic is coming from the study of 175 people experienced relief. So this is coming from taking 75 out of 100, which is going to be 0.75. So we'll have here, calculating the z-score is we'll take 0.75 minus 0.7 all over the square root of 0.7 times 0.3 over our sample size, which was 100. And plugging in this into the calculator, we should get out a 1.0911. And already with this test statistic, you should be getting an idea of whether or not we're going to have significant results, because we have an idea of this number line on our standard normal curve, and to be one standard deviation above the mean isn't that significant. So this gives me some intuition that we're probably going to be getting a large p-value out. It's good to have this kind of intuition of how a z-score lands on the standard normal curve, so that if your p-value comes out incorrect, you can kind of link the two and double check your answer in that way. All right, finding our p-value, we want to use our standard normal curve, and using technology, we want to look at the probability of being equal to or larger than the z-score. So we're looking at the probability that x is more than or equal to 1.0911. And what we're going to get out is a 0.1376. And that right there is our p-value. So when you find that area under the curve, that's our p-value. And to go with our third step, so once we have that p-value, are we going to reject the null or fail to reject? So this is where we compare to alpha. So we want to compare this to 0.05 to compare it to our significance level, and what we're going to see is this is large. And when we have a large p-value, or it's not sufficiently small, that means we fail to reject the null hypothesis. The idea being, where we saw with the z-score and 1 being so close to 0, it's the idea that it wasn't significantly far away, and that created that large area. So this had a high chance of occurring if that proportion is 0.7. So it's not significantly larger than 0.7. So in our wording, we state our p-value. So with a p-value of 0.1376, this is where we just don't have enough evidence to conclude that alternative hypothesis. So there is insufficient evidence. And then we grab wording for the alternative hypothesis, which we could say that that proportion that feel relief is more than 70%, or we're kind of testing effectiveness, so we can't claim that it's more effective. So there's insufficient evidence to claim the new drug is more effective. And that concludes that hypothesis test. What I'm going to do in the next video is show you, using this information, how to use technology to get your p-value out. Still have to evaluate it, and kind of like what we did with confidence intervals, the technology is there to double check your answer. So you'll always want to show all of these steps here, but you can use technology to make sure that p-value is correct.